a scenario. I'm going to set up two scenarios here, and Atkins describes these. Admittedly, it's a bit confusing, but I really like this description of why we call this the free energy. Okay? So this first starts by saying, suppose we have a system. And in this system, we're going to say, suppose that delta U of the system is negative and delta S of the system is negative. And we're going to put together what needs to happen for spontaneity. Okay? And we'll impose that this is the first condition we're going to look at. If the internal energy of the system is decreasing, which is what we'd expect for spontaneity, but suppose that the entropy decreases, could this still be spontaneous? How would we do it? Okay? Well, one thing that we note is for all spontaneous processes, delta S total equals delta S system plus delta S surroundings, and that must be greater than 0 for this process to be spontaneous. So we know right off the bat, if the change in entropy of the system is negative, it can still be spontaneous as long as the change in entropy of the surroundings is greater than the absolute value of the change of the entropy of the system. So in other words, we know that the entropy change of the system is negative, but if I look at the absolute value of that and compare it to the entropy change of the surroundings, and this relationship is true, then I will have a spontaneous process. Okay? So now how do we achieve this? How do we achieve that the delta S of the surroundings is going to increase if the delta S of the system is going to decrease? How do we do it? Okay, well, let's first look at A. So all of this is with respect to A, Helmholtz, but it's the same situation for G, the same situation for Gibbs. Okay, so we know that delta A is delta U minus T delta S. Okay, and we also know for this to be spontaneous, it's got to be less than or equal to 0, that whole chunk. Okay. So, or in other words, what we could say, applying the system to this, we could say delta U of the system must be less than or equal to T times delta S of the system. Okay? And so because we also know that both of these quantities are negative, the change in entropy of the system times temperature cannot be as negative as the delta U. Okay? And so what that means is the following. Okay? So I'm going to expand through this, and I'm going to say dA equals du minus, we recognize that all of that is really dq, which equals dw less than 0. If dw is less than 0, that tells us work is having to be done from the system to the surroundings, and that's exactly what you can see in this arrow. The system is working on the surroundings. So that's one condition that has to be met for all of this to happen. Okay? And you'll also notice there's this condition here that says, well, the work has to be less than the change in internal energy. And that's true because of this relationship. The delta S has to be less than the delta U because of the way this inequality, it has to be less negative than is the change in U. Okay? And so what that means is we cannot supply the same amount of work as we have in internal energy, right? So the work supplied has to be less than the change in internal energy. And so what that also means, to make this condition happen to generate enough change in entropy in the surroundings to keep this process spontaneous, dq has to be much greater than dw, right, to make this happen, okay? That's how this is gonna be negative, right? The dq has to be greater than the dw to make this happen, okay? And it's also going to have to be positive, right, for this to be satisfied. And so in other words, we also then see that a large amount of heat, a really large amount of heat, must be evolved out to the surroundings to generate enough spontaneity to overcome the reduction of entropy in the system. Okay? And so what's happening here is, Atkins puts it very nicely, nature is demanding a tax on you as it's converted into work. And the tax on that is the free energy. Okay? It's the part of the change in internal energy we are used to do, we are free to use for work. And this large amount of heat that has to exit the system into the surroundings is that required component of spontaneity, right? We talked about this with the Kelvin statement of the second law. If our system is going to do work, it has to evolve a ton of heat spontaneously out to have enough entropy change in the surroundings to be spontaneous. Okay? What about another situation? Well, let's impose that delta U system is less than 0 still, but what if now the change in entropy of the system increases? Okay? So it's looking good so far for spontaneous, right? We should just say, well, right away that should be spontaneous. But now what are the physical observables when this happens? So what happens if we have a reduction of entropy in the system as well as an increase of entropy in the system? Excuse me. What are the consequences? Okay? Well, the consequences are that we still have delta U system is less than or equal to T delta S. So this comes from our Clausius inequality. Okay? And so we can see that this is true, that the delta S system will be greater than the delta U system. It's a positive quantity and that's a negative quantity. So that's all good there. Okay? We can also see by relation dA equals du minus dq, which equals dw. And now this is where this gets to be a little tough to gather, because this still has to be negative for this to be spontaneous. Okay? So dw still has to be negative. And that means that it has to be evolving work. The system still has to be doing work on the surroundings. Okay? But this seems a bit paradoxical, because if the system is doing work on the surroundings, there should not be a decrease in entropy of the system, or excuse me, there should be a decrease in entropy of the system, just like in this scenario, right? When the system works on the surroundings, there usually has to be a decrease in entropy because we're exchanging orderly motion for heat, right? Work is orderly motion. When we do work, we're doing something that's more orderly, okay? So there should be a decrease in entropy, but there's not. There's an increase of entropy in the system. And why is that? Well, that is because in order for this to happen, heat has to flow into the system. That's what's going on. You saw the picture there, but I didn't leave it described, okay? In order for this to all be spontaneous, right, delta S system equals Q divided by T, which we know is greater than 0, which tells me dq had to be greater than 0, which means heat has to flow into the system to make this work happen. And even though this seems a bit paradoxical, the way that we can describe this is nature is now providing a tax refund. And that tax refund is the free energy. It's the change in internal energy that we are free to use as work. Okay? So the big picture here, all right, the big picture of what's going on, let me back up here. Where are my equations? Let's see here. Yes, so this is the big picture that's really going on, right? We know that Helmholtz is the difference between internal energy and TDS. So in other words, it is the difference between the internal energy of the system and the heat supplied to the system, okay? And when that quantity is negative, that quantity is free for us to use. It's the free energy, okay? It can be used for chemical changes or physical changes. And when we recognize that these quantities are negative, nature is providing us a tax refund that's giving us free energy that we can use as work. Okay? That is the origin of the name free energy. So Atkins has some lovely prose on this. If I didn't quite do it for you, if you're still left kind of confused by this, take a look at pages 115 through 117 in Atkins. That's where this picture is, and he has a really nice set of paragraphs describing it. Okay.